Welcome to this lecture on Solutions to Exercise 2.4, Question 1 to Question 5 from the book Real Analysis by Bartle and Sherbert.
Welcome everyone to this solution series of the book Real Analysis by Bartle and Sherbert. So today we are going to solve exercise 2.4. So let us take the first question. So this is the first question. In the first question we are asked to show that the suprema of this set 1 minus 1 by n, where n is any natural number, is 1. So let us start with the proof of this question number 1. So let us take this set S equal to 1 minus 1 by n belonging to n. So we need to show that, to show supremum of S is equal to 1. So by epsilon criteria we need to show, that 1 is an upper bound of S, and second, 1 minus epsilon is not an upper bound of S for every epsilon greater than 0. So these two things we have to show. So we have to show that 1 is an upper bound of S, and second we have to show that 1 minus epsilon is not an upper bound of S for every epsilon greater than 0. So for this what we will do? So observe that for each n belonging to n. So if we take any natural number, obviously 1 minus 1 by n is less than 1 because we are subtracting something from 1, so that this number is always smaller than 1. So this implies 1 is an upper bound of S. Next we have to show that 1 minus epsilon is not an upper bound for any epsilon greater than 0. So let us take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So we have picked any arbitrary epsilon. Now we are going to show that 1 minus epsilon is not an upper bound. Okay, so we will use the Archimedean property for this. So by Archimedean property, we know that there exists a natural number m belonging to z positives such that 1 by m is less than epsilon. So we have found a positive integer, a natural number m, such that 1 by m is less than epsilon. So this implies 1 minus 1 by m is greater than 1 minus epsilon, or you can 1 minus 1 by m is greater than 1 minus epsilon. Now 1 minus 1 by m is a member of S because S is the collection of all the elements of the form 1 minus 1 by n, where n is a natural number. So m being a natural number, this 1 minus 1 by m belongs to S. So this implies 1 minus epsilon is not an upper bound of S. Now since the epsilon we chose was arbitrary, so since epsilon greater than 0 is arbitrary, hence by epsilon criteria 1 is supremum of S, that is supremum of S is equal to 1, hence proved. So we have done with the first question. So what we have done is we have used the epsilon criteria. So first we have shown that 1 is an upper bound of S, and then we have shown that 1 minus epsilon is not an upper bound of S for arbitrary epsilon. And to show that 1 minus epsilon is not an upper bound, we have used the Archimedean property. We have shown the existence of a natural number such that 1 by m is less than epsilon. Then we have shown the existence of a member of S which is greater than 1 minus epsilon. So let us now take the next question, which is question number 2. So question number 2 is an extension of the first question. So in the first question we had the set of the form 1 minus 1 by n, where n was any natural number. Now in this case we can vary n as well as m. So we can take different values for n and different values for m, and we have to show that infimum of s. We have to find infimum of s and supremum of s. So let us start its solution. So observe, if you observe, then if you see this number, then you will see that if we take n equal to 1 and we keep on increasing n, then this number gets closer and closer to 1, because this number becomes 0, this number goes to 0 when we keep on increasing m. So when we take n equal to 1 and we take this, so we observe that, in fact, observe that 1 by n minus 1 by m is less than equal to 1 for all nm belonging to n, right? Because this number is smaller than 1, this number is smaller than 1, so difference of these two will be less than equal to 1, obviously. Now also 1 by n minus 1 by m is greater than equal to minus 1, because the two numbers are less than 1, their difference cannot be less than minus 1 for all nm belonging to n. So what we claim is, we will show that our infimum is minus 1 and supremum is 1. So claim infimum of s is equal to minus 1 and supremum of s is equal to 1. Now to we will prove one part and the other part can be proved on the similar lines. So we will show that supremum of s is equal to 1, and then we will on the similar lines we can prove that infimum of s is equal to minus 1. So we will use the epsilon criteria. So we have already observed, so first we will show that supremum of s is equal to 1. So we will use the same epsilon criteria. So note that, because we have already seen that this 1 by n minus 1 by m is less than equal to 1 for every nm belonging to n. So 1 is an upper bound of s. So we have already seen that 1 is an upper bound of s. Next we will show that it is if we take any arbitrary epsilon, then 1 minus epsilon is not an upper bound of s. So let epsilon greater than 0 be any real number. So we will show that 1 minus epsilon is not an upper bound of s. So for that, again we will use the Archimedean property. So by Archimedean property, there exists k belonging to z positive or n such that 1 by k is less than epsilon. So this implies 1 by 1 minus 1 by k is greater than 1 by 1 minus epsilon, that is 1 minus 1 by k is greater than 1 minus epsilon. Now 1 minus 1 by k, we are taking n equal to 1 and m equal to k. So this is a member of s, because s is the collection of all the elements of the form 1 by n minus 1 by m. So we take n equal to 1 and m equal to k. So this 1 minus 1 by k belongs to, since 1 minus 1 by k belongs to s, so this implies 1 minus epsilon is not an upper bound of s. So since epsilon greater than 0 is arbitrary, it follows that one is least upper bound of S, that is supremum of S is equal to 1. So on the similar lines, one can show that infimum of S is equal to minus 1. So there we will show that we have already seen that minus 1 is a lower bound of S, and then we will show that minus 1 plus epsilon is not a lower bound of S, and for that again we will use the Archimedean property. In fact, let us try to show that next. We will show that infimum of S is equal to minus 1. So we have again we know that because we have already seen this part that 1 by n minus 1 by n is greater than equal to minus 1. So we know that minus 1 is a lower bound of S. Now let epsilon greater than 0 be any real number, then by Archimedean property there exists k belonging to n such that 1 by k is less than epsilon. Now we have to show that minus 1 plus epsilon is not a lower bound of S. So this implies minus 1 plus 1 by k. So we are adding something. So inequality will not reverse. So minus 1 plus 1 by k is less than minus 1 plus epsilon. And since minus 1 plus 1 by k is a member of S, because we take m equal to 1 and n equal to k in this case. Taking n equal to k, m equal to 1. Okay. In the last case, when we were proving this supremum of S equal to 1, so here we took n equal to 1 and m equal to k. In this case, we are taking n equal to k, m equal to 1. So since this is a member of S, minus 1 plus epsilon is not a lower bound of S. So as epsilon is arbitrary, so by epsilon criteria, minus 1 is equal to infimum of S. So we have shown that supremum of S is equal to 1 and infimum of S is equal to minus 1. So this completes question number 2. Now let us move to question number 3. So question number 3 is somewhat similar to this second part, the second question only. So this is the third question. We are given a non-empty set S and we have to prove that if U is a number which satisfies the two properties. First property is that for each natural number n, the number U minus 1 by n is not an upper bound of S, and second, for every number n, the number U plus 1 by n is an upper bound of S. Then we have to show that supremum of S is equal to U. So for every n belonging to n, the number U plus 1 by n is an upper bound of S, and then we have to show that supremum of S is equal to 1. So let us start its proof. Given U minus 1 by n is not an upper bound of S. So first property is this, and second we are given that U plus 1 by n is an upper bound of S for all n belonging to n. So for every natural number n, U minus 1 by n is not an upper bound of S and U plus 1 by n is an upper bound of S. We have to show supremum of S is equal to U. So we will show that U so from first part we will conclude that no number smaller than U is an upper bound of S, and second part we will show that any number greater than U cannot be the least upper bound of S. So then we will be able to show conclude that U is the least upper bound of S. So let us start. So since S is non-empty and bounded above, so by completeness property of R, S has a supremum, say W. We have got a supremum of S which is W, so that is W is equal to supremum of S. Our claim is to show that W is equal to U. Claim W is equal to U. Now by law of trichotomy, we have three possibilities. First is W can be less than U, or W can be equal to U, or W may be greater than U. So we will reject these two cases. We will say that W less than U is not possible. We will say that W greater than U is not possible, and hence we will conclude that W is equal to U, that is U is equal to supremum of S. So this is what we will try to show. So if W is less than U, then take epsilon equal to U minus W by 2, which is greater than 0. So what we are basically doing is, so this is the number line, if we have the number line, and this is our U and this is our W. So then what we will do is we will take epsilon equal to U minus W by 2. So this will become the W plus epsilon. This number will become W plus epsilon, and then we will, by Archimedean property, we will find a natural number such that 1 by n is less than epsilon. 1 by n less than epsilon means, or this is U minus epsilon also. This number is U minus epsilon. Then we will find a number which is U minus 1 by n somewhere here. That will be U minus 1 by n, and by Archimedean by given hypothesis, we know that this number is not an upper bound of S. So this, it will contradict the fact that W is an upper bound of S. Then by Archimedean property, there exists K belonging to N such that 1 by K is less than epsilon. So this implies U minus 1 by K is greater than U minus epsilon, which is equal to so if we take U plus epsilon, so it will be U plus W by 2, which is equal to W plus epsilon, which is greater than W. So this number U minus 1 by K is greater than W. Now by given hypothesis, the given condition, first condition, hypothesis 1, U minus 1 by K is not an upper bound of S, which contradicts the fact that W is an upper bound of S and U minus 1 by K is greater than W. Fine. So what we have done is we have taken, so this technique we use it at a lot of place. So if we take any number which is smaller than it, we take the difference of the two, and either we take half or half the distance or something smaller than half. So we may also take u minus vw by 3 also. Then this number u minus epsilon will be greater than w. So we have shown that if w is less than u, then we arrive at a contradiction. So this is not possible. So next we will take the case when w is greater than u. Now if w is greater than u, then take epsilon equal to u minus w by 2, which is again greater than 0. Sorry, w minus u by 2 this time, because this time w is positive, w is greater than u, so w minus u is positive. Then again so we take this epsilon, then again by Archimedean property there exists m belonging to n such that 1 by m is less than epsilon. So this implies u plus 1 by m is less than u plus epsilon, which is equal to u plus w by 2, which is equal to w minus epsilon, which is less than w. Now by given hypothesis, second, we know that u plus 1 by m is an upper bound of s. So we have a number which is smaller than w and is an upper bound of s. So which is a contradiction. Contradiction to the fact that w is equal to supremum of s and w is greater than u plus 1 by m. Hence the only possibility that is possible is, hence w is equal to u, because we have rejected the two cases. So if we took w less than u, then we arrived at a contradiction. So in that case we took the epsilon equal to u minus w by 2. When we took w greater than u, then we took epsilon equal to w minus u by 2, and in that case also we arrived at a contradiction. Hence both are not possible. So the only possibility is w equal to u, that is u is equal to supremum of s. So we are done with the third question. Now let us take the next question, which is question number 4. So this is the question number 4. So in this question we are given that S is any non-empty bounded set. We are given a positive number A, and we have to show we are given a set, another set which is defined using S, and it is AS equal to, we multiply all the elements of S by A, and then we get the set AS. We have to show that infimum of AS is equal to A times infimum of S. So we can take the A outside this infimum. Similarly, we will show that supremum of AS is equal to A supremum of S. So provided A is positive, so if A is positive, then we can take this A outside. Okay, but if we take the negative number, then the infimum becomes supremum and supremum becomes infimum. So what if you want to see this in a more simpler word, what it means, it's supremum of positive number alpha s is equal to, or you can say is this is alpha times supremum of s. But if you have negative number, so then it will become infimum of S. So whenever you take minus outside, then your inequality this changes. If you take the plus sign outside, then there will be no change. But if you take the minus sign outside, then supremum will become infimum. So this is what you need to remember. If you are taking minus outside, just like if you are multiply any inequality, if you multiply any inequality, then if so it is similar to if a is less than b and we multiply this inequality by a positive number, then there will be no change, right? If c is greater than 0, but if c is less than 0, then inequality reverses, right? So similarly, if you take positive term outside or you take positive term inside, then there will be no change in the, when there will be no change, infimum will remain infimum, supremum will remain supremum. But if we take minus sign outside or if you take minus sign inside, then supremum will become infimum, infimum will become supremum. So this is what we need to show. Okay, so we'll prove the first part and first part first, and then we will prove the second part. So in the first part we will prove only the infimum part. Supremum part can be done on the similar lines. Similarly, in the second part also we will prove the infimum part, and supremum part can be done on the similar lines. So let us start with the proof of a part. So we have to show, given a is greater than 0, we have to show supremum of as. We have to show that supremum of as is equal to a times supremum of s. So this is what we need to show. Okay, so this one is very easy to prove. So first we will assume that let w star equal to supremum of as and w equal to a times supremum of s, or w equal to supremum of s. So we have to show that basically w star is equal to a times w. Now by definition of supremum, s is less than equal to w for all s belonging to s, right? Every member should be less than equal, because w is an upper bound, so every member is smaller than w. So if we multiply by a positive number, then inequality will not change. So again this is less than equal to w. Now this is the set of all elements of as, right? This is the set of all elements of as. So as is less than equal to aw for all s belonging to s. This implies aw is an upper bound for the set since a is greater than 0. We are multiplying this by a positive number, so inequality will not reverse. So aw is an upper bound for the set as, hence w star being the least upper bound is less than equal to aw. Okay, now next we will prove that aw is less than equal to w star. For this, again, as w star is supremum, so as is less than equal to w star for all s belonging to s, right? Because w star is supremum of the set as. Again, as w star is supremum of as, so as is less than equal to w star for all s belonging to s. So this implies s is less than equal to 1 by a times. So basically we are multiplying this by 1 by a being positive, 1 by a is positive, so inequality will not reverse. So this is less than equal to a times for all s belonging to s, and this implies 1 by a times w star is an upper bound for this set s. So for this set, 1 by a times w star is an upper bound, and this implies w is less than equal to 1 by a star, 1 by a w star, and this implies aw is less than equal to w star. So from 1 and 2 we have aw is equal to W star, that is A times supremum of S is equal to supremum of S. Similarly, we can prove that infimum of S is equal to infimum of A times AS. So this property can be proved on a similar line. So we will not prove it here. Similarly, it can be proved that infimum of AS is equal to A times infimum of S. So this part is complete. Now let us take the next part. So let us prove this B part in this. We take this second part. So we'll prove that infimum of BS is equal to B times supremum of S. So we're given B is less than 0. To show infimum of BS is equal to B times supremum of S. So again in this case what we will do, we will let W star equal to infimum of BS and W equal to supremum of S. So by definition of supremum, same thing we will do just like we done in the last question. So by definition of supremum, S is less than equal to W for all S belonging to S, right? Because W is supremum of S, so every member of S is smaller than W. Now we will multiply by B. Now multiplying by B is because B is negative, so it will reverse the inequality. So this implies BS is greater than equal to BW for all S belonging to S, since our B is negative. So we are multiplying by a negative number, then equality will reverse. And what does this implies is, this implies BW is a lower bound for the set BS. So for this set BS, the BW is a lower bound, and W star being the greatest lower bound has to be greater than equal to BW. So this implies W star is greater than equal to BW. Again, now we will take the W star, definition of W star, again as W star is equal to infimum of BS. So B times S is greater than equal to W star for all S belonging to S. So what does this implies is, now we will multiply by 1 by B, and because we are multiplying by 1 by B and B negative means 1 by B is negative, so inequality will reverse. So this implies 1 by B times W star for all S belonging to S, since B is negative implies 1 by B is negative. So we are multiplying the inequality by 1 by B, and 1 by B being negative reverses the inequality. So inequality is reversed. So this implies 1 by B W star, because it is greater than S for every S. So 1 by B W star is an upper bound of S. So this implies W is less than equal to 1 by B times W star, because B is, because this is an upper bound and W is least upper bound. So further this implies that, because now what we will do, we will multiply it by B. So on multiplying by B, the inequality will reverse. So BW is greater than equal to W star. So from maybe what we can do is, maybe we can call it as star and we can call it as double star, because we have already used 1 and 2. So from star and double star, we conclude that W star is equal to BW, that is infimum of Bs is equal to B times supremum of S. On the similar lines, one can prove the other part of this question. On the similar lines, it can be proved that supremum of Bs is equal to B times infimum of S. So this completes question number 4. Now let us take the last question, which is question number 5. So this is the question number 5. We are given a set of non-negative real numbers. So S contains non-negative real numbers. Non-negative real numbers means either the number is negative, no, 0, or it is positive. We don't have negative numbers in S. And we take T to be the set of all those elements, all the squares of S. We have to show that if U is equal to supremum of S, then U square equal to supremum of T. And then we have to give an example that shows the conclusion may be false if we restrict if the restriction against negative numbers is removed. That is, if we take negative numbers in S, then this result may fail to hold. So let us see this. So first we will prove this result, and then we will see which example will show that the conclusion will fail if we remove the restriction of taking negative numbers in S. So let us start with the proof. So given U is equal to supremum of S, to show U square is equal to supremum of T. T is the set of all squares of elements of S. So first we will show that U square is an upper bound of S, and then we will show that no number smaller than U is an upper bound of S. So since U is equal to supremum of S, X is less than equal to U for all X belonging to S. So every member of S is smaller than U. So this implies X square is less than equal to U square for every X in S. Since both X and U are positive, X is greater than equal to 0. Right? X is a member of S and X is greater than X, so X is greater than equal to 0. And if we have two positive numbers, and if we take their squares, so the inequality will be preserved. Okay, so because this inequality is preserved as both are positive numbers, both X and U are positive, so this inequality is preserved. If one of them was negative, then we may this inequality may fail to hold. So this implies U square is an upper bound of S. So we have shown that U square is an upper bound of T. U square is an upper bound of T. Now we have to show that any number smaller than U square cannot be an upper bound of T. Or let W be an upper bound of T. So we have to show that U square is less than equal to W. That is, X square is less than equal to W for all X belonging to S. So this implies X is less than equal to root W for all X belonging to S, because W is positive, right? X is also positive. Again, since X is positive, so this inequality will hold. We can take the square root and inequality will be preserved, because X is positive and W is also positive. So this implies root W is an upper bound of S, and this implies U is less than equal to root W. So this implies u square is less than equal to w. Again, since u is greater than 0, so we can square it and the inequality will be preserved. Hence, u square is least upper bound of t. This implies u square is equal to supremum of t. So this we have proved that if u is a supremum of s, then u square is a supremum of t. Next, we will give an example where we will remove the restriction of negative numbers in S. That is, we will consider the negative numbers in S, and then we will show that supremum of S or u square may fail to be the supremum of S. For let S equal to, so we have to include the negative number, and we will make sure. So minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2. Let us take this. So then t is the square of all, so square of all is 25, then 16, then 9, then 4, then 1, 0. Again 1 is already there, 4 is already there, so this is our set t. Now supremum of s is 2 and supremum of t is 25, which is not equal to 2 square. Hence, so if we allow the negative numbers in S, then the result may fail to hold. The result holds only when the numbers are positive, and we can see also from the proof that positivity of the numbers are used everywhere. Here also this inequality is preserved only because x is positive. Here also we can see this inequality is preserved because x is positive. So all these inequalities are preserved only when the number is positive. So if we allow the negative numbers, then we can see that the result may fail to hold. So this completes question number 5. So in this video we keep till here. In the next video I will solve further questions. Till then, take care. Have a good day.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.